Hi everyone, it's week 4, so I'm going to make a new video of some of the tougher homework problems. There are 3 problems that I've selected this time. Um, if you have any others, like always, please let me know in the Q&A discussion board and I can film another video, but these 3 are kind of long, so I thought they made for a good selection for this week. All right, I'm going to start with number 9. Suppose that a box contains 7 cameras and 4 of them are defective. A sample of 2 cameras is selected at random. Define a random variable x as the number of defective cameras in the sample. So we're going to consider x as choosing a defective camera. So like choosing a defective camera is a success in this case, which is kind of strange. But for the purposes of this problem, that's the way we're going to go. So we're only going to select 2 out of these 7 for our sample. And for the probability distribution, we need to first come up with our possible outcomes. And since we only have a sample of 2, and the choices are either defective or working, we only have a very limited number of outcomes here. So we're going to say the outcomes are we could get 0 defective cameras, we could get 1 defective camera, or we could get 2 defective cameras in our sample. So I'm going to go ahead and write those in my X column. Let's see. So maybe I need to click on draw here. There it goes. So 0, 1, and 2 are my possible outcomes here. Now we have to figure out the probability that we'll get any of these outcomes. So this is the tricky part. So we have to consider this a situation that involves dependent probabilities because we've got, say, the first choice is going to be a camera out of the 7, and then the second choice depends on what happened in the first choice. So we have to remember, okay, in the first choice, we got a defective camera, or we got a working camera, and consider that for our probability for the second choice. So let's start with the 0 case. So this means we got a sample of 2 cameras and none of them are defective, or both of them are working. So we'll say the first probability is going to be 3 out of 7 because there are 3 working cameras out of the box of 7. So the probability of selecting a working camera in that first choice is 3 out of 7. We're going to multiply because this is an AND case. We want a working camera and another working camera. And the probability of selecting the second camera out of the box that's working is going to be 2 out of 6 because now there's just 2 working cameras left in the box and 6 total cameras because we removed 1 from that first choice. So my probability is going to be 3 over 7 times 2 over 6. I'm going to get out my calculator. 3 over 7 times 2 over 6 is 0.143. I'm rounding to the nearest thousandth here. All right, I'm going to skip down to the 2 case at the bottom. The 1 case is the tricky one, so I'll save that one for the end. The 2 case is very similar to the 0 because this time we need a selection of a defective camera and then another defective. So first selection, there's 4 defective out of 7. Now for the second choice, there's only 3 defective left and only 6 total cameras left. So 4 out of 7 times 3 over 6 is 0.286. All right, now for the 1 case. And this one's tricky because there's 2 different ways we can end up with 1 defective camera in our sample of 2. So we could either get the defective camera first and a working camera second, or we get that working camera first and the defective camera second. So we have to consider these two possibilities. So it's either the first case or the second case. So when we have an or situation in probability, that means we're going to be adding probabilities together to get our final result. So case one, I'm going to say we got our defective camera first, which is 4 out of 7, and a working camera second. And there are 3 working cameras and 6 cameras that are left. The second case, we're just going to reverse them. We're going to take our working camera first, which is 3 over 7, times a defective camera second, so there's 4 defective out of 6. So now we're just going to multiply those together. You can see that they're actually going to end up being the same result on number 1 and number 2 because they both end up being 12 over 42. So that's that 0.286. If we add those together, I'm taking the long version of the decimal, 0.285714, and so forth, add them together, and round to the nearest hundredth is 0.571. So if you add up those probabilities, it should come to 1, and that's what happens every time when you have a probability distribution. The probabilities always have to add to 1. All right, the last question on number 9 is what is the expected value of x? So this is basically asking for the mean of the probability distribution. So the mean of the probability distribution is basically asking, in the long run, if we keep repeating this probability experiment over and over, like we have the 7 cameras, we take 2 out, we see how many defective ones do we have. We put them back, draw 2 more, keep repeating this experiment over and over again, counting up how many defective ones we have, and averaging those numbers together. So in the long run, we would expect how many defective cameras out of our sample of 2 would we get. So the way we come up with the expected value of a probability distribution is we just multiply the rows together, the x times the p of x, and then add up all those results. So 0 times 0.143 is just 0. Multiply the second row, 1 times 0.571 is just 0.571. And the last row, 2 times 0.286 is 0.572. If we add those together, we get 1.143. And that's the expected value. So in the long run, if we keep repeating this over and over again, we would expect to get an average of 1.143 defective cameras in our sample of 2. All right, moving on to number 15. So number 15 has a lot of parts to it. I just wanted to show off a calculator for this one that's in the calculator's notes in the modules because many of these problems, they have some very cumbersome formulas, very tricky to do by hand. It's very easy to make one little error that messes up the whole thing. So we want to rely on technology for these types of problems. So we have an estimated 47.3% of Kickstarter projects are successfully funded. Assume each Kickstarter project is independent. A random sample of 15 Kickstarter projects are followed. Let X be the number of Kickstarter projects that are successfully funded. Calculate the following. So the first thing it's asking is the mean and the standard deviation of this random variable. So we have to figure out what type of distribution this is. If you go back into the notes, we have um, an example where every trial or every possibility or selection has an equally likely chance of happening. In this case, there's always a 47.3% chance of any Kickstarter project being successfully funded. And the other thing we need is that independent statement there. So that means that any project is still has a 0.473 probability of being funded regardless of what happened to any other project. So uh, one project getting funded does not depend on what happened with another one. So if it's the same probability for every trial and all of the trials are independent, we have a binomial probability distribution. So I'm going to open up that in my lecture notes. Let me expand this a little. Now I can move the window over. In my module for videos and calculators, I'm going to click on binomial. And for these first few problems, we're going to use the probability of x equals a number. So we'll get to the other choice a little later. For this one, we want a probability of a success being 0.473, which is the decimal probability of 47.3%. The number of trials was 15. And from the problem, the first thing that it's asking for is the probability that exactly 7 of the choices were selected. So let me put in 7 for my x. Scroll down and calculate. And the nice thing is this calculator gives me my mean and standard deviation of my distribution. So I would put those in my first two slots, and it gives me all of the probabilities based on 7. So equal to, less than or equal to, greater than or equal to. So I don't have to calculate those all separately. Any question that it asks for on that problem, you just have to change the number of successes and you'll get your answer there. So the last one is asking me the probability that x is between 5 and 8 inclusively. So it includes 5 and 8 as possibilities for the number of Kickstarter projects that were funded out of 15. So I will go back to that calculator. In the drop-down menu, I'll choose the between. Minimum is 5, maximum is 8. And calculate again. And my answer for that one would be 0.678. So again, this would have been incredibly difficult to calculate by hand, but we're relying on technology, so it's not too bad. All right, one more to go. Let me scroll back down, get this back to where I can write. And we're going to do question 27. So Priya is deciding which standardized test score to report to the colleges she's applying to. Priya took both the SAT and ACT and wants to report whichever score is higher relative to the test. We have our SAT score as 1290. SATs have a mean of 1,000, standard deviation of 200. Her ACT score was 28, and ACTs have a mean of 18 and a standard deviation of 6. So we're going to calculate z-scores for her two test scores here. A z-score is a score that tells us how many standard deviations above or below the mean a person's score is. So this is a great way to compare two different data values that are not on the same scale. So we have all the information we need. We have the score, the mean, and the standard deviation. There is a calculator for calculating z-scores. I'm just going to do it by hand because it's not terribly difficult. The z-score is always equal to the data value, which we call x, minus the mean, which is that mu symbol, over the standard deviation. So first one we're going to calculate is her SAT score. So her SAT score was 1290, so that's our data value. Going to subtract the mean, which was 1000, and divide by the standard deviation, which is 200. Do that subtraction first. 1290 minus 1000 is 290 over 200. Oops, I gotta go down here. Which is 1.45. Now let's do it for the ACT. Data value is her test score, which is 28, minus the mean, which is 18, divided by the standard deviation, which is 6. 28 divided by 18 is 10. 10 divided by 6 is about 1.67. So on the SAT, she scored 1.45 standard deviations above the mean, and the ACT, she scored 1.67 standard deviations above the mean. So she actually did better on the ACT because she did better relative to other students that have taken the test, and she scored a little bit higher in terms of standard deviation. So if she was sending this to a college and she could only pick one, she would want to report her ACT score because she did better relative to the mean. All right, thanks for hanging with me for that whole video. Again, if you want to see any others, let me know. Otherwise, good luck on your homework and quiz, and we'll be back at it again next week. Take care.